I am live now. Okay, Ragnar Lothbrok. Just a dream. Video downloaded. Yep, I am live. And now, for today, in assembly language, we had to do the questions for chapter number 6. That is multiplication. Right, it was chapter number 6, right? I'm not being stupid. Chapter, let me see. Abstract data types, which was chapter number 5. Then we have this chapter number 6. Oh, we actually completed chapter number 6. My bad. And now moving on to chapter number 7. We did all the theory, and now we have to do the exercises. And here was this 700 line C code. That is crazy. Yep. Now we go on to the exercises. Let me fix all of these. Yep. Question number 1. Let me go to the folder where I do my questions, and in chapter 7.s here, multiply minus 90 by 105 using signed 8-bit binary multiplication to form a 16-bit result. Show all of your answers. Multiply minus 90 by 105. Okay, well, I will not use the dot data section. I will use the dot data section to print the result. So let me do that. Format string as keys, and the answer is, or not the answer, but some number multiplied by some other number gives some third number, and then new line, and then dot. In the dot text section, I will declare a thing called main, which is global, and align the commands at 4 bytes. And in the main, let me first of all store the frame pointer and the link register here onto the stack by pre-incrementing the stack by 16 bytes and initializing the 0th register with minus 90 and the first register with 105. Wait, I have to use okay, 8-bit binary multiplication, using 8 signed bit binary multiplication. Let me store them in the first 32 bits. That is, I guess, the best I can do. Again, you cannot access 8 bytes, 8 bits, right, of a register. The least I can get is 32 bits. Now I want to multiply these numbers, and I know that one of them is a negative number. So if one of them is a negative number, I have to take its 2's complement, and then multiply these two numbers, 105 and the complement of 90, and then the result that I get, I have to get its two's complement. That would be the final answer. How do I multiply bits? Yes, I need a few registers. What was the algorithm for multiplying these? The algorithm was, what was it? I need a accumulator register. Yep, and I need to see the smallest bit in W1. Yeah, I would Let me initialize a register. I will have the answer in W2. Okay, and here I will have a loop, and in the loop I will compare the I have to get the smallest bit from W1. Yep, I have to get the smallest bit from W1, and to get that I will take its and save the and in, let's say, the third register W3, take the and of W1 with 1. Now I will have the LSB of 105 in the 0th register, in the third register. Now I want to check the LSB. Compare W3 with 1. Now, if the LSB is 1, I want to add the contents of the 0th register into the second register. So, conditionally select or conditionally add. Can I mm, yep. Let me see how to conditionally add in AArch64 assembly. Conditionally add, is there a function for conditionally adding? Adds conditionally select. Okay, yeah, that is what I was hoping I would get. I cannot add conditionally, so first I have to save the addition sum into another register and then I can conditionally select that. I cannot add directly conditionally. So I will add the contents of the 0th register. I will save them in the 4th register, add the contents of the 0th register, and what? Where am I getting the answer? In the second register. Now, after that, I will compare and then conditionally select and store in the second register. If I have the bit as 1, I will be checking for equality. If it is equal, then the second register will contain the new value that is in the 4th register. Otherwise, it will retain its value from the second register. Now, yep. After that, I would like to logically shift left the contents of the 0th register, save them in the 0th register by 1, and logically shift right the contents of the first register by 1 by 1 bit. Is that it? Is there anything else that I would like to do? Yep. And at the end, I will compare the contents of the first register with 0, and I will branch if not equal to the loop. And here at the end, when I know that I have the answer in the second register, I will like to print that. And shit, I would also like to retain these original values. So, well, I can simply add them here, get them here. Let me get the address of the format string in the 0th register. For that, I will first get the page address, then page address of the format string, and add to it the page offset. And now I need to make storage on the stack by 32 bits because I want to store 3 integers. So let me put 32 bits there. First, I will store the pair of, let me, before that, get the values in the let's say third and the fourth register. So move into the third register. The first number, that is minus 90, and move into the fourth. Wait, god damn it. Into the fourth register, the value 90 and 105, not minus but normal 105, and store them onto the stack. Store the pair, not W3. I will be storing them in the whole 64 bits. So store the third register and the fourth register contents onto the stack. That should be good. And then store the contents of the second register, which contains the result, onto the stack by giving it an offset of 16. That makes sense. And then simply call the printf function, intf printf function. And after that, let me clear the stack by giving it back what I took. And yes, store. I will load back the frame register, the frame pointer and the link register from the stack, and then add 16 back to it, and then move in the 0th register 0 and exit with that value. Now this should work. Chapter 7.s. Okay, I misspelled chapter. Chapter 7 to chapter 7.s. Now clang chapter 7.s and put the output in the dot. Oh, it worked in the first try. Oh shit, god damn it. Is the answer correct? 90 into 100 is 9,000. 9,000 plus 5 into 90, 450. That it actually works. But why is it not printed out? Okay. I put 2 backslashes here. Yep, now this should work. Clang /out. Okay, so first question done. Now multiply 166 by 8-bit multiplication to form an unsigned 16-bit result. Show all of your work. Well, I can use this exactly the same algorithm that I used in the previous question. Like do the same thing. Print this here, like copy this and comment this one out and just switch the numbers. 105 and the other was 166, and even here at the end 166, and clang and /out. So what, let me calculate in mind. What is 166 into 105? That should be easy. 1,166, 1,000, 16,600, and 166 into 5, 160 into 5, 800, 800 plus 30, 830, 830 plus 16,600, that would be 17,480. 17,430. 80 plus 6,600. Yeah, 17,430. Yep. So the answer is correct. Now, write a section of AArch64 assembly code to multiply the value in first register by 13 using only shift and add operations. Well, that is what I have been doing. What the heck? Oh shit, my Russian keyboard is at work. Shit, how do I switch back? Shit, how do I switch back? I forgot the key. Shit, okay, I can change from here. There was a shortcut to change all of that. Yep, now it works. Um, in chapter 7, and again, the same goddamn thing. Copy this, go to the top, and paste the same code here, and go down. Let me comment all of this out. Comment C, go back up, and change the numbers. Let's say I have 13 here and any number, let's say 10 here, and I will get the answer. And I need to store them and change them here also. This is not a very good design, so before doing all of this, let me store their values. Move into which registers am I not using? Am I using the fifth register? No, I'm not using the fifth. I can use that. Move into the fifth register the value of the zeroth register, and move into the sixth register the value of the first register. And then at this point, instead of moving them, I will get the values from move into the third register the value from the fifth, and move into the fourth register the value from the sixth register. And this should work, and it does. Actually, that is cool. The following code will multiply the value in the x with c. What is c? Let me see. Yes, we did this yesterday. Um, this takes in the value of 0 and adds to it left shifted value of 0. That would be equivalent to multiplying it by 1 1 in binary, that is 3. So I have 3x in the first register, and to 3x I am adding left shifted twice value of the first register. If I left shift by twice, that is multiplying it by 4. So I multiply the content of the 0th register by 4 and add them to 3x. So 4x plus 3x, that is 7x. So answer is 7. Let's check. In the code below, the contents of the 0x register are being multiplied by a constant. What is the constant? Let's see. I don't know if ChatGPT will get it, but from my side, the answer is 7. Let's see. Yep, 3x. That is cool. 3x plus 4x, 7x. So the answer is 7. Yep, that is cool. ChatGPT got it. Now, question number 5. Show the optimally efficient instructions necessary to multiply a number in register 0 by the constant 67. Okay, I want to multiply by 67. 67. And how is 67 in binary? Well, 1 for 64, 0 for 32, 0 for 16. After, yes, I would need 3. So 32 is 0, 16 is 0, 8 is 0, 4 is 0, 2 is 1, and 1 is 1. This is 64 in binary. So first, I will need to multiply the number by 3. Let's suppose if I have the number in this zeroth register, I would add to it its left shifted value by 1. Yep. Uh, that would be equivalent to multiplying by this part, and then to this part I will add the multiplied value by this part, and to multiply to get the value for this I would have to left shift the contents of the X register by 1, 2, 3, 4, 5, 6. So now to the new value of the zeroth register, I will add left shifted value by 6. That is just 2 instructions to get the final answer. And how do we write that in code like this? First of all, let me comment all of this out and go to the top, and let's yep, copy all of this and go below, paste it, put it down, comment, and here, yep, this is the format string, and the value is 67. So I will only need the zeroth register, and yep, I will not even need a loop. I don't need this, and actually I can change quite a few stuff here for calling printf. Yep, this much would be the same, and let me store the number here, num dot askeys. Oh, wait, I can just store it into the zeroth register. So the number would be moved to the zeroth register. The number 67 multiplied by 100. Okay, and to do that, first I will move with add and store in the zeroth register the value. But I will also require the original value, so I will store in the first register the value of the zeroth register added by itself after logically shifting left by 1, and then add and save to the zeroth register the value of the first register, that is multiplying it by 3 and left shifting the value of the zeroth register by 5. Yep, no, 6. Now the zeroth register should contain the answer, and at that point I will move the answer along with the other values onto the stack. For that I will get some space on the stack like so, and move to the first register. What is the first value that I want to add? The first value that I want, the multiplicand is the original value of the X register, which is now lost in the chaos. So let me move that to the first register just here, and then I can here do this 67. Yep, and then store to the stack, store the first and the second register contents onto the stack, and then store the answer, which is in the zeroth register, onto the stack by giving it an offset of 16. Okay, and now yes, let me get the address in the zeroth register for the format string, which is fmt at page, and now I will add to it the page offset. That is good. After adding the page offset, I can call the printf function, right? Yes, I can call the printf function. Now, after that, I have cleared the stack, loaded back the pointers, and did all the things. But that should work. That should work. Let's see. Store. Okay. Now, chapter 7. Yep. Whereas TP. Yes, this should be R. Yeah. Okay. Why is it 300 now? Why does it say 300? I'm doing this 100 and this is being stored in the first register is getting updated here at this point. So yeah, I should not be stupid. Make this the second register, and here instead of getting value like this, let me do this. Yep, this should work properly, and it does. Okay, we did that. Now we want to show how to divide 78 by 6 using binary long division. Wait, it is not, the question is not telling me to do it in assembly, and it was not telling me to show all of your work. I think in these two questions, it meant that I have to do it by hand. That is crazy. Okay, and this also wants me to do it by hand. Binary long division. 78 by 6. What would happen? I can write an algorithm for that easily, and divide and minus algorithm. Demonstrate the division. Now, okay, I will write the algorithm in the next question. Demonstrate the division algorithm using a sequence of tables as shown in figure this to divide 155 by 11. Demonstrate the division algorithm. Okay, using this algorithm, I have to divide two numbers. God damn it. Shit. Yep. Using that algorithm, I have to divide 155 by 11. When dividing by a constant y, is it desirable to have m as large as possible to get the most precision in dividing, to get the maximum amount of precision that we can get. And my stream is not stuck. That is good. So demonstrate the division algorithm of sequence multiplying 155 by 11. So that is doable. Of course, that is doable. Go to the top, and I will define them here. The format is string, which will store an ASCII that says a value divided by another value gives another value, and then new line. And then in the dot text section, I have something global main, and then I will align it by 4 bytes, and then describe it, uh, storing the pair frame pointer and the link register onto the stack by pre-incrementing by 16 bytes. And then I would like something. What do I have to do now? multiply, divide, move into the zeroth register 11155 and move into the first register 11. What is the answer? I don't know. Okay, now I need to divide them. I do not exactly remember the algorithm at the top of my head, so let me devise, let me in some way remember, recall, and derive the algorithm. I need to do some things. What did I have to do? Yes, I had to increase the dividend. Yes, there were two parts. First part uh, makes the dividend this, the divisor, left shift its value till it is greater than the dividend, and then I will keep right shifting the divisor, and whenever I see that the divisor is less than the dividend, I will subtract the divisor from the dividend and then continue till till the divisor is zero, right? Yeah, till the divisor is zero, right? Yep. No, no, no. Till the count is zero. Uh, Count is another register which holds the number of times that we originally left shifted the first register. So here, left shift, let's call it. So I will at the start compare. This will be a post loop. So logically shift left and store in the first register the contents of the first register and one, and then add to the second register, store to the second register one, and then compare the first and the zeroth register and branch to the left shift label only if branch to the left shift label only if the first and second register branch only if less than or can it be equal to? Nope. No, no, no. Branch only if the contents of the first register are less than the uh, zeroth register, and after that I will have a second loop that would do subtraction sub loop. In this, what I will do is compare the contents of the first and the zeroth register, and I have to, well, what are the things that I have to do no matter what conditions are? Logically shift left the contents of the first register by 1 byte and compare the counter that is in the second register with XZR zeroth 0 and branch if less than to sub loop, that is if compare becomes -1 I will branch. Yep. Is that correct? No, I will not branch if it becomes -1. Okay, but I will branch when it is 0. Yeah, I will branch when it is 0. Okay, that makes sense. And also subtract from the counter 1 at the end of every loop. And here comes the juicy part. Now, if the divisor is smaller than the dividend, only then I want to subtract the divisor from the dividend. And to do that, conditionally, I first have to store that subtraction in, let's say, the third register. Subtracting from the first, the second register, and then conditionally select and store in the 0th register the either the third or the 0th register if the first is smaller than the 0th, that is less than or equal to. Now this should work, I guess. And then at the end I would like to print the result, and to do that, let me store these values into the registers that I am not using. Let's move into the 4th register the content of the 0th, and move into the 5th register the contents of the 1st register, because I will be needing them afterwards. And where the heck is the answer? Shit, I need a register to store the answer, so let's make that the 4th register. This will store the quotient. Now at the start, I would like to logically shift left the contents of the 4th register by 1, and on comparing, I would like to conditionally increase and store in the 4th register the contents of the 4th only if less than or equal to. And at the end, I will have the answer in the 4th register. But before that, let me move into the 6th register, the 0th register contents, and here. So now I have the answer in the 4th register, in the 5th register, and the 6th register. So I have the values that are to be put up on the stack. So let me get some space on the stack, 32 bytes, and store the pair from 6th and the 5th register onto the stack without any incrementation, and then store the contents of the 4th register onto the stack with an increment of 16 with an offset of 16, and then I will get the address into the 0th register for the format string by first getting its page address and then adding the offset to it, page offset, and then I can just branch link to printf. Now let me clear the stack by adding 32 to it, and then I will load back the frame pointer and the link register back from the stack, and then add 16 bytes which I took from the stack, and also exit with the exit code 0 and return. That should work. Store pair, okay. Chapter 7, line 38. Here, this should be R. Clang, and do I see? Yes, I do see the answer. It seems to be goddamn 0. Why is it 0? When is the time that I am increasing the contents of the 4th register here? So what am I comparing? The contents of the divisor and the dividend. And if the divisor is less than the dividend, then I am increasing the value of the fourth register, and the fourth register initially contains 0. And I am also left shifting the value of the fourth register every time, which is also correct. Then why am I getting 0 as the answer? Is the 16-bit offset too long? Nah, I don't think so. It could be because an integer takes 32 bits to be stored, which is 4 bytes, and I am only storing 2 integers. Then should this be 8? I don't think so. Yeah, it should not be 8. Yep, it should not be 8. It was, it is only 16 only. Or maybe something like this, and then making it 8. Let's see. That is also wrong. Oh, yep, that is also wrong. What can I do here? So where does the mistake lie? Lie. This is lie. Yes. Hmm. 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 Yep. 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 And I am also comparing the contents of the second register 0 and also subtracting. I keep subtracting the value of the counter. I wrote this algorithm yesterday and it was working just fine. But today I have some problems. Let's focus on the first left shift part. Am I doing this correctly? First, I left shift the contents of the first register by 1 bit. Okay, that is correct. And then I add 1 to the counter, and then I compare the left shifted divisor with the dividend. And if the divisor is still less than the dividend, then I start this again. And when this divisor becomes greater than the dividend, then this loop will end. So there does not seem to be any problem with this part. And now here, in the subloop. At this point, I have a divisor which is greater than the dividend. Then what do? I logically shift left the fourth register, which is the quotient, and it is empty. And then I subtract from the dividend the divisor and store it in the third register. And then I compare the dividend with the divisor. Then I compare the divisor with the dividend, and if the divisor is less than or equal to the dividend, then I update the dividend with the subtracted value. Otherwise, with its original value, it does not change. And in the quotient, if the I check the same condition, that is, if the divisor is less than or equal to the dividend, then I increase the value of the fourth register. Otherwise, I do not. That is also cool. And then I am subtracting 1 from the counter, and I'm logically shifting left. Ah, the same goddamn mistake that I did yesterday. I have to logically shift right. This was the exact same mistake that I did yesterday. And what is the problem? Shit. Why is it still not working? Logically shift right the first register by 1 and then compare the second register with 0, and if the second register is less than equal to the subloop, then go back to the subloop. Logically shift left and logically shift right and logically shift left the first register. Yes, that is all correct. What is the problem? What is the problem now? Is it the way that I am storing the result onto the stack? I am getting 32 bytes of storage on the stack. Then I am storing the sixth and the fifth registers onto the stack, and then the fourth register, which is the answer actually, onto the stack, and then I am getting the address of the format string in the zeroth register, and then branching off to the printf function, and then adding back to the stack pointer, that is clearing, popping off the values that I used on the stack, and then I'm loading back the frame pointer and the link register from the stack into their respective registers, and then I am exiting with exit code 0. Then what is the problem then? Just recompile and run it again. That is the first instinct. Recompile and run it again. The second instinct, and when they both fail, recompile and run again. No. Then I actually start thinking about where you went wrong. I will mess up the inputs. Let's make this 10 and 2, and let's see how that works. That is still 0. Why is that 0? I am at the end using the contents of the fourth register to print the answer, and the fourth register is initialized by 0, and then I am conditionally increasing the contents, the value of the fourth register. And I know that this is the correct format because I did this yesterday, right? Divide by subtracting. Yep. In this, in the second part, I did this divide. Conditionally increase, and here I am checking for greater than. Somehow it's because the values have flipped. This one was working just fine. Yep, I'm adding 1 and logically shifting left one time. The first loop is exactly the same, and then I have a pre-test loop where I first check for 0 and only then move. Check if the counter is 0, and if it is, then I move down. What is this? What is these? This chapter 6. Okay. This is chapter 7. After logically shifting left the contents of the first register of the fourth register, that is the quotient, only then I add value to it. Otherwise, I keep its original values. And why is it not getting increased at any point. Like, why am I getting 0 here? Why isn't it never increasing? Is the first register never less than 1? Never less than the, is the divisor never getting less than the quotient? Huh. Huh. Well, I am logically shifting right. The divisor every time. So it should at one point get smaller than the quotient, than the dividend, because I am shifting this right. I would like to see how many times this loop is actually running. Mm, 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 mm. The zeroth and the first register, I'm comparing them, and if the divisor is less than equal to 0, only then I am updating the third register, the 0th register, which is the divisor, and the fourth register. Maybe before doing that, I should do this. I don't think that that would make any difference, and it should not make any difference. Yes, so that is stupid. It should not make any difference. Now I want, what the heck? Okay, how do I check what is going wrong? Let me recompile and run it as you should. There is still problem. Should I turn this into a post in pre-test loop? But how would that help? That this should not matter if it is a pre-test or post-test loop. This should run the same and should not matter. Mm, 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 mm. How much time has it been? Shit. And then we have these behemoths of questions. So, shit. Okay, let me do this. Compare the contents of the first, that is the divisor, with the dividend, and before that I am subtracting the divisor from the dividend and saving it to the third register. Okay, and then I am increasing the fourth register if the divisor is less than the dividend, less than or equal to, and then also saving to the dividend the subtracted value of the divisor if it is less than or equal to 0. Less than or equal to the divisor if the divisor is less than or equal to 0. Less than or equal to the dividend. Then what is the problem? Where am I going wrong? I'm subtracting 1 from the counter every time. That is also good. And then I'm logically shifting right 1 bit of the first register every time in the loop. Yes, that is also necessary. Yes, that is necessary. And then I'm comparing the counter with 0. Let's see what will we get. I have 2 and 2 and 10 here. So when I logically shift left 2 by 1, I get 4. And then if I do it again, I get what do I get? I get 8, and then if I do it again, I get 16. So at the end of this loop, I in counter I have 3, and in as the divisor I have 16, and in the dividend register I have 1. I have 10. Then I move here. After this instruction, the fourth register is still 0. After this instruction, the third register now contains -6, that is 10 minus 16. And after this, I compare 16 with 10, and if 16 is less than 10, update, which is, it is not. So, and this also is not true because 16 is not less than 10. Then I subtract 1 from the counter, I get 2. And here I logically shift right the first register so that I get 8. And here I compare 2 with 0, which is not equal to, is not less than 0. So I move back at the top of the loop. Here I logically shift left 4 by 1, which is still 0. And then I subtract from 10. Yes, from 10 I subtract 0. I subtract 8 and store 2 in the third register. And then here I am comparing 10, 8 with 10. And if 8 is less than or equal to 10, then I am increasing the fourth register, which now becomes 1. And here, then I am doing the same with the zeroth register. Zeroth register becomes 1 as well, becomes 2 after this instruction. And here at this point, counter becomes 1. And this, so this I would like it to be less than or when it is equal. I do not want it to go back when it is 0. Well, I don't think this would help, but let's just see. Yep, as I thought. Why is this messing up? Am I messing up with the printing part? Storing at the frame, storing in the stack, subtracting 32 from the stack pointer, and then I am storing a few values, 6th and the 5th register onto the stack, and then also, yes, this is correct. This is not wrong. This is correct. I have to add 16, not subtract. Right? Yes, right. And then I'm getting the address for the format string in the 0th register. That is also correct. And then I am branching off to printf. What is the problem? Let me exit with the contents of the 4th register, just so I have another way to check. Echo $sign question mark echo question mark $sign echo $sign question mark. So yeah, the exit code for that is actually 0. Why? Chapter 7 let me put the contents of which register. The first register. What do I expect to see at there? Let's see. Clang and dot slash out and echo. The first register is also 0, and so. Oh, let's do this. Why the heck is it becoming 0? Why is it not increasing? Why is the fourth register not increasing? I do this. Wait, I can do this instead of this. Comparing it with zero, I can compare the contents with 100, which is a guarantee that it will be smaller. Then I should see at least something. Yes, I see 1. But why do I see only 1? Is this loop running only once? That would make sense. That this loop is only running once and I am comparing. Okay, let me exit after this. I would like to see the counter. How is the counter? Move the contents of the counter into the, let's say, 7th register, x2, and then I will exit with the contents of the 7th register. Clang and this, and then okay, I see 3 in the counter, which is good. Why is this happening? There is only a logically shift right. The first register. Wait, let me see the content of the first register after that. 0. That is interesting. I'm logically shifting left the contents of the first register by 1. Shifting left should increase the value, but it is not. Why is it not increasing the value? That is strange. And I'm only using the first register here to store 2 into it, and then here to logically shift it left, and then here to compare it. But why is it becoming 0? Why is it becoming 0? Let me see what is the value of the first register at this point. It should be 2. It is 2. Okay. Why is this becoming 0? Why the heck is that happening? And when it is 0, then why is it only running once? Why am I not getting bigger values there? Something wrong is happening with this code. Something is not adding up. Okay, this is taking a lot of time and I will look into it in my free time. And for now, let us move on to the next questions, right? Because it has taken a lot of time, like 20 to 30 minutes on this single question, and we cannot do that. And this is a very elementary question, and we cannot spend 20 to 30 minutes. Well, not at least not on stream, right? So I will get back to it on my own. When dividing by a constant value, why is it desirable to have a m as large as possible? Because m contains the significant digits from the divisor. So if m is large, then we have more significant digits from the divisor, and thus our answer will be more accurate, more precise, and that is why we need m to be as large as possible. Modify our program from exercise 5.13 in chapter 5 to produce a 128-bit result rather than a 64-bit result. What was the question in exercise 5.13? Shit. Exercise 5.13. 5.13 seems like the last question. For a large factorial, function is slow. However, a lookup table can add to the function to avoid performing deep recursion every time. This technique is commonly known as memorization and deep learning, dynamic programming, uh, but is sometimes called dynamic programming. The following C implementation of the factorial function uses memorization. Modify your AArch64 assembly program from the previous problem to include memorization. Well, the thing is that when I wrote that function, it does not require memorization. It works as fast, but let me go back to chapter 5. This question, this is the one. It scans and then print the factorial. Prints the factorial. Now I would like it to print a 128-bit factorial. That is crazy. That is literally crazy. Eh, that is crazy. I have a string here and a scanf string here. Shit, that is crazy. Instead of scanning a 32-bit integer, first of all, I will make it scan a long hexadecimal number. And then I will also be printing a long well, no, D is fine. The input will be a 32-bit number, but the output is as this is long unsigned. And let me make it h2 numbers. Scan. This part scans the function. Okay. What does it do? Scan f, and in the 0th register I have the address for it. I have the answer in the 0th register, and then I load the answer onto the stack, and then I compare the contents of the first register with one. And if it is equal, then I print factorial. Okay. And I add 16 to it, to the stack pointer, because I subtracted 16 here, and loading back the pointer, and then I return. Okay, and here printf, print fact. This function has in the zeroth register the factorial value, and it gets the answer in the zeroth register factorial. What does factorial do? Factorial, yes, this is the function that I would like to modify. What does this do? This function moves 1 to the first register, yes, and compares the zeroth register with 1, and if zeroth register is less than that, then I do not do anything. Right, right. I can even remove these lines. Right, yep. And if not, then I multiply. Yeah. So the thing is that I will be storing the LSB in the second register and the MSB in the first register, like that. And then I would like to multiply. I would like to multiply and store. First of all, I will just multiply the LSB normally, and for the MSB, how can I multiply the MSB? If there is a carry, I want to multiply 264-bit numbers, right? Yep, yep. I can do S, that is, this will also update the state counter, program state, P state register, and the this contains the LSB which goes here, and then conditionally multiply. For addition it is simple, but for multiplication I have to check if there is a carry. Wait, nope. I can store long. I guess that is the correct input, and store it into the first register, multiply this and the second register. Nah, not that, but how do I pass on the carry? Right. This seems okay. Well, multiply long. Okay, let's see what is next. Is that me pushing out multiply long? The stream quality is not good, or it is good. That is not the point. The point is that I am unable to do this question, and maybe because I'm not trying, well, not because exactly because I'm not trying hard enough. I'm not focusing. Okay, I have to rethink my goals. Why did I start doing any of this? Because when dividing by constant, why is it desirable to have a good idea of how all this works? A single book will not make me understand everything. And I have a different book that I will also be reading later, which also concerns itself with binary things, and that is why I can go a little softer with this book, because this gives me basis to start understanding that other book. So yes, I can go a little softer with this and focus more on assembly than focusing on the intricacies of binary algebra. Yep. So yeah, we can move on to question number 10. Modify our program from, yep, we not did that, but we how would you do this in C? Well, we can use a long 128-bit number, right? That C handles it for this, right? The begin shift left chunk function shown in listing 7.6 in AArch64 assembly and measure the performance improvement. How can I measure the performance improvement? What I feel like is that these remaining chapters are more mathematics than assembly language, and thus we can skim over them without going into a lot of details. And these exercises concern themselves more with binary multiplication than with assembly language. And my goal with this stream, with these series of streams, is to understand assembly language, not binary multiplication and binary things. For binary things, I have a different book which I will be reading and not streaming because I have a physical copy of that book, and that will take me a lot of trial and error to understand everything in that. So my goal with this stream is to understand assembly language and not how binary things work. So that is my focus with this, and I do not have to feel bad when I do not understand binary multiplication or binary related topics in this stream. So I will keep that in mind, and because this also requires time, right? This stream is has been going on for 20 streams. This series has been going on for 20 streams, and I'm just halfway through the book. So I want to complete this series this month, and it would not be possible to complete it if I were to go into the detail and understand every single binary thing, which is not that much related to assembly language. That was the original goal of this stream, of these series. So if it is not too much assembly, I can softly kind of get an idea and not become like professor in it. Well, I'm not becoming a professor in any of the topics that I have done till this point, but the idea is that if it is more mathematics than it is assembly, then I can be soft with it. That is the idea, and that also gives me speed in learning assembly. That is good, right? I'm learning assembly to understand coding, programming, how that helps, and I will be learning binary also, but at some later point, I have some other plans for learning binary. So yes, we can move on to the next chapter here, and let me take a little break, and I will be right back. You were watching Jordan Peterson there. And now, yep, this non-integral mathematics. The whole idea is to get when you're starting to learn about a new field is not to get into the details, but get an overview, a big picture about what the thing is that you are getting into. And then after getting a big picture, you can get into the intricacies, divide that big picture into smaller sections, and you can focus solely on those sections, and one by one you can improve over those sections, and the whole picture will have more detail, right? But the idea in the starting is to get a big picture about how things are and to get an idea, even if you don't understand them perfectly with every intricacies and details, then it is fine. You can always get back to it when you are focusing on that particular section. Now, let's start with this non-integral mathematics, that is floating point mathematics. And this is going to be a big ass chapter. Let's see. Chapter 7, introduced methods for performing computation using integers. Although many problems can be solved using only integers, it is often necessary or at least more convenient to perform computation using real numbers or even complex numbers. For our purposes, a non-integral number is any number that is not an integer. Many systems are only capable of performing computation using binary integers and have no hardware support for non-integral computations. In this chapter, we will examine methods for performing non-integral calculations using only integer operations. Base conversion of fractional numbers. In section this one, explain how to convert integers in a given base into another. We will now extend the method to convert fractional numbers in radix point notation. A fractional number can be viewed as consisting of an integer part, a radix point, and a fractional part. In base 10, the radix point is also known as the decimal point. In base 2, it is called the binomial point. That makes sense. In base 10, it is decimal, and in base 2, it is binomial point. For base 16, it is hexamal point. Crazy. In base 8, it should be 8 is octimal point. Octimal point. The term radix point is used as a general term for a location that divides a number into integer and fraction parts without specifying the base. So, fraction numbers have an integer part followed by a point, a radix point, and then a fractional part. One point, one arbitrary base to decimal. The procedure for converting fractions from a given base b into base 10 is very similar to the procedure used for integers. The only difference is that the digit to the left of the radix point is weighted by b0, and the exponent become increasingly negative for each digit right of the radix point. The basic procedure is the same for any base b. For example, the values this can be converted to base 10 by expanding it as follows. This has power 0, power 1, power 2, 2, 1, 0, and then minus 2, minus 1, minus 2, minus 3, minus 4. Okay, and I just add them all like that, and I have it in decimal. Likewise, the hexadecimal fraction, this can be converted to base by expanding it as follows, like this. Okay, okay. Anyways, to arbitrary base to decimal. That is how it is done. Okay, that makes sense. Decimal to arbitrary base. When converting from base 10 into another base, the integer and fractional parts are treated separately. The integer and fractional parts are treated separately. The base conversion for the integer part is performed in exactly the same as it was in before, using a repeated division by the base b. The fraction part is converted using repeated multiplication. For example, to convert the decimal value this to binary representation, convert the integer 5, 10 into its binary representation, which is 101. Multiply the decimal fraction by 2. The integer part of the result is the first binary digit. So to the right of the radix. So this multiplied by 2 becomes this. The first binary digit to the right of the binomial point is 1. So far we have reached this equals 101.1. Multiply the fraction part by 2 once again, and I get this being converted into this. So I get 0 here. The second binary digit to the right of the binomial point is 0. So far we have this equals this. Multiply the fraction part of x by 2 once again. So for this I get 1.1. I will add 1 there again, and then I will multiply zero point 0.5 with 2, and I will get this. The fourth binary digit to the right of the binomial point is 1, so we have now this equal to this. Since the fractional part of x is now 0, we know that all the remaining digits will be 0. The procedure for obtaining the fractional part can be accomplished easily using a table as shown below. Yes, 1011. Yeah. Putting it all together, this equals this. After converting a fraction from base 10 into another base, the result should be verified by converting it back into 10. The result from the previous example can be expanded as this, and we do get the correct decimal number for the binary number that we converted. Now, converting decimal fractions to base 16 is accomplished in a very similar manner. To convert this into base 16, we first continue the integer proportion by repeatedly dividing 16 by to yield this. When we then repeatedly multiply the fractional part extracting the integer portion of the result. So we will multiply it by 16, right? Yep, multiply it by 16. Multiplying this by 16, I get this, so it becomes 3, and multiplying this by 16, I get 12. 12 in hexadecimal is ABC, right? 12 is C, so yes, 12 is C, so I get C there. Okay, that is makes sense. This tabular method works for fractional notation as well as radix point notation. For example, when converting this to base 6, we convert the integer portion by repeatedly dividing by 6, which results on 23. Then we convert the fraction portion as follows. Here. Okay, when converting this number to base 6, we convert the integer portion by repeatedly dividing the result by 23, which results in 23 or 23, like this. And then we convert the fractional portion as follows. I have this, and I will multiply that by 6 to get 2 whole, so integer part becomes 2, and I multiply with then this 3 by 4 by 6, and I get 4 halves, and then the half with 6 to get 3, so the answer becomes 0.243. 0.243, 23.243. To check the result, we can convert it back into base 10 as follows. Into base 10, yeah, we can convert it back into base 10, and we do get the actual result. Okay. Shit, this is going too deep, right? 8.1.2.1. Shit, bases that are powers of 2, can we convert them directly? Converting fractional values between binary, hexadecimal, and octal can be accomplished in the same manner as with integer values. However, we must take uh, how must however, care must be taken to align the radix point properly. Yep, as with integer, converting from hexadecimal or octal to binary is accomplished by replacing each hex or octal decimal with the corresponding binary digits from the appropriate table shown in below, like very early in the book in chapter 1. But now we are at chapter 8, pretty halfway there, right? More than halfway. there. For example, to convert this to binary, we just replace 5 with this to binary. So 5 in binary is 0, 1, 0, 1, and A means 10, and 10 in binary is 1, 0, 1, 0. And then we have C. C is 12, and 12 in binary is 1, 1, 0, 0. So 0, 1, 0, 1, A is 1, 0, 1, 0, 1, 0, 1, 0, and C is 1, 1, 0, 0. Yep. And 4 is 0, 0, 1, 0. Sorry, yes, 0, 1, 0, 0, 0. My bad, 0, 1, 0, 0, and 3 is 0, 0, 1, 1, and B is 11, which is 8 plus 3, that is 1, 0, 1, 1, and 1, 0, 1, 1, B. So using the table, we can immediately see that this equals this with a radix point in the middle. This method works exactly for the same converting from octal to binary, except that it uses the table on the right side of that. Converting fractional numbers from binary to hexadecimal or octal is also very easy using the tables. We do not need the tables. We can just calculate this at the fly. The procedure is to split the binary string into groups of bits, working outwards from the radix point, then replacing each group with its hexadecimal or octal equivalent. For example, to convert this to hexadecimal, we have the first four, 1, 2, 3, 4, 1, 2, 3, 4. This is 2, and the later 4, this is, what is this? This is 7, 7, 2, and yep, 7, 2, and here we will have 1, 0, 1, 0, 1, that is 10, and 10 in hex is A, okay, and A, and we have this, which is 14, I guess. 14 is E, so 7, 2, A, E. To hexadecimal, just divide the number into groups of 4 bits starting at the radix point and working outwards in both directions. It may be necessary to pad with zeros to make a complete group on the left or right or both. Our example as follows is this: a complete group, complete group, complete group, and here we added a 0 at the end. Now each group of 4 bits is converted to hexadecimal by looking up the corresponding hex digit in the table on the left side of figure 1.3. This yields this number. Yep. This yields this. For the octal, binary would be grouped as follows. Yeah, and this is what is this? This is 5, this is 3, this is 4, this is 2, this is 6, and this is 1. So 1, 6, 2.5, 3, 4. 1, 6, 2.534. Yep. Now each group of 3 bits is converted to octal by looking up the corresponding digit in the table on the right, but we do not need the table. We can calculate on the fly. This yields this. Note that the conversion to octal required the addition of leading and trailing zeros. Yep. Fractions and bases. Okay. Fractions and bases. Fractions and bases. One interesting phenomena that is often encountered when using radix point notation is that fractions which terminate in one base may become non-terminating repeating fractions in another base. One okay, which terminate in one base may become non-terminating repeating fractions in another base. For example, the radix point binary representation of the decimal fraction 1 by 10 is non-terminating repeating fraction as shown in example 18. Non-terminating repeating binomial. Binomial. Multiply this by 2, I get this. Then this will not end. I will keep at getting 0, 0, 1, 1, 1, 0. And then if I multiply 4, this will never end because I start I got back where I started 4. So the pattern from here will start repeating 0, 1, 1. 00110011, and it will always keep repeating. Yep, 00110011. The resulting fractional part from the last step performed is exactly the same as in the second step. Therefore, the sequence will repeat. If we continue, we will repeat the sequence of steps 2 to 5 forever. Hence, the final binary representation will be this. We can put a bar to signify that this keeps repeating. Because of this phenomena, it is impossible to exactly represent 1.1 and many other fractional quantities as binary fractions in a finite number of bits using radix point notation. Then rounding numbers. The fact that some base 10 fractions cannot be exactly represented in binary has led to many subtle software bugs and incorrect results when programmers attempt to work with currency and with other quantities as real valued numbers. In this section, we explore the idea that representation problem can be avoided by working in some base other than base 2. If that is the case, then we can simply build hardware or software to work in that ways and will then be able to represent any fraction values precisely using a finite number of digits. Okay, but is there a base like that for brevity? What the heck is brevity? I've heard it a few times now. Brevity meaning concise, the state of being short and quick. Okay, and concise meaning giving a lot of information in a few words. Brief me on how the military expenditure is going on. For brevity, we will refer to a binary fraction quantity as binimal and a decimal fraction quantity as decimal. We will look to how whether there are so decimal does not mean point radix point in any number. Decimal means radix point in base 10, specifically in base 10. Okay, we would like to know whether there are more non-terminating decimals than binimals. More, we would like to know whether there are more non-terminating decimals than binimals. Okay, so that Okay, if there are more non-terminating decimals than minimals, more non-terminating binimals than decimals, or neither. Okay, so then we can choose that base and make our hardware work in that way, right? Okay, since there are an infinite number of non-terminating decimals and an infinite number of non-terminating binimals, we could be tempted to conclude that they are equal. However, that is an oversimplification. The infinities are not the same. Shit, that is what I was referring to. That is, we are here for assembly, not for this. Okay, this is hardcore maths. And I would be able to understand this if I give it a few days, but that is not the point. Understanding mathematics like this is not the point. I can get an overview idea without the implementation details, an overview theoretical idea of what this is about. But if I try to go into more detail than that, that would take a lot of time. And if I do that, that would actually take a lot of time. So, but it is not that I will never understand this. The thing is that a time will come when I will understand this too. But right now, it is assembly that we are focusing on here. However, that is an oversimplification. If we ask the question differently, we can discover some important information. A better way to ask the question is as follows. Is the set of terminating decimals a subset of the set of terminating Benimals or vice versa or neither? That is a good question. Is the subset of terminating decimals a subset of terminating benimals or vice versa? Terminating decimals, we can represent them using finite numbers. Is that a subset of terminating benimals? Hmm. Or vice versa? We start by introducing a lemma, which can be used to predict whether or not a terminating fraction in one base will terminate in another base. We introduce the notation this, which means it reads as x divides y to indicate that y can be evenly divided by x. Yeah, y can be evenly divided by x. So point 1, that is point 1, can be evenly divided by 10, but it can also be evenly divided by 2. So I don't think that is the problem. Lemma 1. If x, where x is between 0 and 1, terminates in some base b, okay, a product of primes, then this a product of primes in a base b, a product of primes, then x equals nx numerator x denominator d, and dx equals this, where pi is the prime factors of b, where b is a product of primes, and pi to the power ki. What the heck is ki? I don't know. And pi's are the prime factors of b, and this is a lemma. Okay, dilemma. Oh, lemma is that I have decided this, and dilemma is I cannot decide anything. Ah, that I guess makes sense. If x if x where x is between 0 and 1 terminates in some base b, and b is a product of primes. That is, if it is 2, then it is the product of 0 and 1, and if it is 3, it is the product of 1 and 3. If it is 6, it is a product of uh, its prime factors are 1, 2, 3, 6, 1, 2, 3. Its prime factors are, and if it is 8, its prime factors are 1 and 2, and if it is 15, then its prime factors are 1, 3, 5. Then x equals x numerator divided by x denominator, where xd is this. Okay, proof. God damn it. X equals numerator divided by denominator, and denominator equals this, where pi are the prime factors of p. Then denominator divided by numerator multiplied by k max, where k max is maximum of k1 to n. But what the heck is even k? Like, is there like, is it saying that there exists some k for which this thing is true? But we also have not put a finger on the numerator maximum of the case. So x equals nx upon dx into x. This terminates after kmax or few divisions. Dx power x. Okay, or few divisions, let x equals nx terminate kx, then division, since dx does not evenly divide. Okay, this is too mathematical, and this does not seem like assembly for what I signed up for. This is pure binary numbers, right? And I do not want to get into binary numbers because that is not my target. So let me just read. The set of terminating binary binomials is a subset of terminating decimals. Huh. The set of terminating decimals is the set of terminating binaries is a subset of set of terminating decimals. That is, we can represent less numbers in binary infinite digits than we can represent in decimal. Proof is here, right here. Then the set of terminating decimals is not a subset of terminating binomials. That is, they are not equal. Shit. Then the set of terminating binomials is a subset of terminating binaries, but the set of terminating decimals is not a subset of terminating binaries. That is, there are the amount of numbers which we can represent in binary uh, using fixed number of digits is higher than the amount of numbers which we can represent in fixed number of characters in decimal, in binary. So, and that is the gist of this whole part till here. Now, implications. What are the implications for that? Theorem 1 implies that any binary fraction. Yep, stream is going perfectly smoothly. Theorem 1 implies that any binary fraction can be expressed exactly as a decimal fraction. Any binary expression fraction can be defined exactly as a decimal fraction. Yes, as a decimal fraction in radix point notation, but Theorem 2 implies that there are decimal fractions which cannot be expressed exactly in binary radix point notation using a finite number of bits. Every fraction, when expressed in lowest terms, which has a non-zero power of 5, every fraction, when expressed in lowest terms, which has a non-zero power of 5, in its denominator can be represented in binary with a finite number of bits. Another implication is that some fractions cannot be expressed exactly in either binary or decimal. For example, b equals 3235. Then any number with the denominator this terminates in base 30. However, if k2 is not equal to 0, then the fraction will terminate in neither base 2 nor base 10, because because 3 is not a prime factor of 10 or 2. That is theory, and not even theory, that is advanced theory, I would guess. Advanced mathematical theory, this whole thing. It is not, it is a bit scary actually, but we get some idea of what they are trying to say. Now, yep, let's get till here. Fixed point numbers. Why are they called fixed point? Another implication of the theorem is that the more prime factors we have in our base, the more fractions we can express exactly using radix point notation. Okay. For example, the smallest base that has 2, 3, and 5 as prime factors is 30. Using that base, we can exactly express fractions in radix notation that cannot be expressed in base 10 or in base 2 with a finite number of digits. For example, in base 30, the fraction this will be terminated after one division. Share. That is 15 is 3, 5. What the heck? 15 is 3 into 5. Okay. To see what the numbers will look like. Let us extend the hexadecimal system of numbers to represent digits beyond 9 so that we get this character for base 30. This, okay, since this equals this, the fraction can be expressed precisely as point m. Likewise, the fraction this, okay, let me see, 13 by 45. I can multiply this by 2 to get 90, and 26 is q. So point q, the fraction this is this, but terminates in base 30. Since this equal to this number will 908 k not q. Okay, this number will have 3 or fewer digits following the radix point. To compute the value, we will have to raise it to higher terms using 30 square as the denominator given to us. This is equal to this. This is equal to this. And now we convert it to base 30 by repeated division. That is divide the by repeated division. This equals 8 with the remainder 20. So we are representing 260 in base 30, but why are we doing this? Because we need, because this is greater than 30, therefore we would be needing two places, and for two places I have to multiply it by a square of 30, that is 90. So I have to convert this into the form 900, not 30. So I can convert this into 30 or 900 or 27,000. Although base 30 can represent all fractions that can be expressed in base 2 and 10, there are still fractions that cannot be represented in base 30. For example, 1 by 7 has the prime factor 7 in its denominator, and therefore it will only be terminated in base that is a prime factor of the base, the fraction 10, 1 by 7. Wait, okay, 1 by 7, 1 by 7 is 1 by 10, and 10 is has 2 and 5 as prime factors. So I need to, yes, yes, yes. The fraction 1 by 7 will terminate in base 10, base 14, base 21, and base 42, and an infinite number of other bases, but not in base 30. Since there are an infinite number of primes, no number system is immune from this problem, no matter what the base computer works in. There are fractions that cannot be expressed exactly with a finite number of digits. Therefore, it is incumbent upon programmers and hardware designers to be aware of a round of errors and take appropriate steps to minimize their efforts. For example, there is no reason why the hardware clock in a computer should work in base 10. They can be manufactured to measure time in base 2 instead of counting seconds in tens, hundreds, and thousands. They can be calibrated to measure in fourths, eighths, sixteenths. This would eliminate the rounding off error problem in keeping track of time. For this reason, the most common crystal clock oscillators used for driving watches, clocks, and other timekeeping devices are carefully calibrated to run at a frequency of this, which is 2 raised to the power of something big. I guess this is 2 raised to the power of, when you raise 2 to the power of 10, you get 1,000, and to 11, you get 2,000, and then again 4,000, 8,000, 16,000, 32, 2,000, so add 4, 15. 2 to the power of 15 is this, right? 2 to the power of 15. Yes, 32,768. Okay, now this fixed point numbers and how much of the chapter is actually remaining. We are at page 246 and 8.3 floating point numbers. This is going to be interesting. Floating point numbers, and then we have Q notation, something called Q notation, fixed point operations, and this was fixed point numbers. Okay, and then how we can perform operations, that is also cool. And then we have what do we have? Shit, operations are big ass long. Fixed point input and output, and then we have compute sine and cosine. That is too crazy. And then we have a big ass program, and we have then floating point numbers. Okay, what is the difference between floating point and fixed end? All of that will be cleared in this chapter, and then we have chapter summary at page 292, and we were at page 230, we were at page 240, 246, and 292. That is good. We got this. And for today, that would be the end of the stream, except I have to stream for 1 more minute to complete my 2 hour mark. Should there have been dropped frames in the stream? How is that? That is good. We got this. And yep, there are no dropping frames right now. I think I should increase the lighting and stuff. And okay, I'm planning to start another series, another YouTube series, in which I will read this book. This is by Brian Kernighan, and so there are other books also by Brian Kernighan. The Elements of Programming Style, Software Tools in Pascal, C programming language, with Terence Ritchie, which is amazing book. And Awk programming language, the Unix programming environment. That is a good book. I think I will read that. Ample, a modern programming language for mathematical programming. Okay. The practice of programming. D is for digital. Hello World, opinion columns from the Daily Princeton, the Go programming language. That is a good book. Understanding the Digital World and Millions, Billions, Zillions. Well, these are good books by Brian Kernighan, and I will be reading them too. Maybe I will read them over here on the stream. But for now, that is the end of today's stream. Why? Is there something else that I would like to do? Nope. Bye. That is the end. Thank you.